Hey, hello, good morning. So today's Saturday, and I found this beautiful problem early morning. I was just going through random texts, and then I found this masterpiece, which remained hidden from all of us. Gems. It's really a gem. You should try this book. First, let me clarify that this is not a paid review. Okay, I am just telling because I read this book and then I found that the problems here are damn lovely. So I would like to go through this problem here. So if you look at this, we have f of x is a polynomial with integral coefficients. If both f of 1 and f of 2 are odd, then we have to prove that for any integer k, f of k is not equal to 0. So let's prove this. So suppose there exists k belong to integer, okay, such that f of k becomes 0. So if f of k becomes 0, this implies x minus k is a factor. So x minus k is a factor of f of x. That means I could write f of x is equal to, so x minus k into q of x. So here q of x is again a polynomial. So for some q of x, polynomial with integral coefficients, polynomial with integral coefficients. And now if you see here, so f of 1, so I'll put x is equal to 1, so I get 1 minus k into q of 1. And if I put 2, I get here, so 2 minus k into q of 2. And now from these two, we come to know that 1 minus k and 2 minus k, these are consecutive. So these two are consecutive. So this implies one of them has to be odd. One of them has to be even or odd. You could say any. So now if one of them has to be even, so this implies if I take 1 minus k to be even, so case 1. So if my 1 minus k is even. So if my 1 minus k is even, so that means even into q of 1 is going to be even. So this implies f of 1 is even. And if I say that 2 minus k is even, so in that case, I'll be getting f of 2 to be even. So f of 2 is even. So in either case, I get a contradiction. So which is a contradiction now. So that means our assumption is wrong. So assumption, towards our assumption, we assume that k belong to integer and f of k is equal to 0. So our assumption is, so this implies there does not exist any k belonging to integer such that f of k is equal to 0. Now, if you have followed this problem, this makes so much sense now. Eventually, why? Because if you take, instead of 1 and 2, if I replace by some other numbers, if I just take two consecutive integers and I do the same thing for, say, 3, 4, 4, 5, minus 1, minus 2, then the same results hold, basically. So we could actually give the general form. General form would be, so if p of x is a polynomial, so if p of x is a polynomial of degree n, and for p belong to integer, okay, f of p and f of p plus 1 are odd, then p basically not f, it's p we have taken because this is my polynomial. So polynomial p, this p is a small value, okay, so p of p and p of p plus 1 are both odd. Then p of x is equal to 0 cannot have integral roots. So we could justify. So if P of x is a polynomial of degree n and for P belong to integer, so if I just take two consecutive integers, so that P of P and P of P plus 1 are both odd, then P of x is equal to 0 won't have integral roots. And the proof is exactly same as the this argument. Same argument we can take. So we'll be writing P of some integer k and then P and P minus 1 are both again consecutive. So one of them has to be even. So the same story will follow. So if this followed, then now we can think of this problem. So we have to find the number of integral solutions of this equation. So I'll take this polynomial P of x is equal to x to the power 15 minus 14x power 7 plus 81x to the power 3 plus 8x plus 1. So directly I would see here P of 0, which turns out to be 1. And I'll find out now P of 1. P of 1 turns out to be 1 minus 14 plus 81 plus 8 plus 1. So which is 81, 8 plus 1, 9 plus 81 plus 9, 90 plus 1, 91 minus 14. 7 and 7. So 1 and 77 both are odd. So P of 0 and P of 1 are both odd. So this implies P of x is equal to 0, does not have an integral solution. I hope you followed. Thank you so much for watching. Happy learning. Have a nice day.